Hello everyone, I'm Tharshen Subramaniam from University Technology Petronas, Malaysia, and I'll be presenting my project on predictive and classification models for cognitive frailty using blood and gut microbiome data. This project is supervised by Associate Professor Dr. Nasrin binti Badruddin. First, to understand this project, we need to know what is cognitive frailty. It's a geriatric syndrome characterized by coexisting physical frailty and cognitive impairment without a clinical diagnosis of dementia or Alzheimer's disease. Basically, it means having physical frailty and cognitive impairment at the same time, but the cognitive impairment hasn't reached the stage of dementia or Alzheimer's disease. Unlike dementia, cognitive frailty is potentially reversible, making it a crucial target for early detection and intervention. So why is it a growing concern? Aging population increases risk of cognitive frailty. Cognitive frailty results in higher risk of disability and dependency as it leads to functional decline, hospitalization, and mortality. Cognitive frailty is a strong risk factor for progression to dementia. There are three problem statements for this project. The first is current diagnostic approaches are reactive and not proactive. Current diagnosis of cognitive frailty is often made when function decline is already present, limiting intervention effectiveness. Existing screening relies on observable cognitive decline rather than prediction. The second problem statement is the limitation of clinical-based approaches. High cost and resource limitation in traditional diagnostic tools make early screening not feasible for large populations. The third problem statement is the need for non-invasive and cost-effective predictive model. Blood and gut microbiome biomarkers are underutilized for cognitive frailty prediction despite studies linking to cognitive decline and frailty. No current predictive model fully integrates blood or gut microbiome biomarkers with machine learning for early cognitive frailty detection. There are four main objectives for this project. The first is to develop a machine learning-based predictive model for cognitive frailty progression using blood-based biomarkers. The second is to develop a machine learning-based classification model to distinguish frail and non-frail individuals using gut microbiome data. The third is to identify the most relevant biological features, both blood-based and microbial, that contribute to cognitive frailty prediction and classification. The fourth is to evaluate and compare the performance of different machine learning algorithms using appropriate metrics. So let's move on to methodology for blood biomarkers-based predictive models. There are four main components, which are data preprocessing, model development, model evaluation, model refinement, and optimization. For data preprocessing, first, participants with missing data were removed, and then participants were matched across time points to calculate cognitive frailty severity score, which is basically the differences between their cognitive frailty status from point 1 to point 2. And then delta features for each biomarkers were generated. For model development, regression models were trained to predict changes in cognitive frailty severity score. The models trained were linear regression, standard support vector model, random forest, and XGBoost. Models were trained using 80-20 train test split with 5-fold cross validation. For model evaluation, MAE, RMSE, R-squared score were used to assess and choose the best performing models based on balanced performance across all metrics. For model refinement, the feature selection was adjusted using importance rankings, hyperparameters were tuned, and this iteration continued until model achieves clinically acceptable level of accuracy and generalization. For methodology on gut microbiome-based classification, for data preprocessing, the participants were classified into frail and non-frail categories based on their cognitive frailty status. The raw abundance data were normalized and converted to relative percentages, and samples with missing data were removed. For model development, the classifiers trained were logistic regressions, support vector model, multilayer perceptron, random forest, XGBoost, LightGBM, and CatBoost. They were trained across 5 taxonomic levels, which are phylum, class, order, family, and genus. The models were trained using stratified 80-20 train test split. For model evaluation, accuracy, precision, recall, and F1 score were used to assess and choose the best performing models. On balanced performance metrics, feature importance rankings were analyzed to determine top contributors. For model refinement, the feature selection was adjusted using importance rankings, the hyperparameters were tuned, and this iteration was continued until model achieves clinically acceptable level of accuracy and generalization. For results and discussions, here's the performance summary for blood biomarkers-based prediction. We can see that the XGBoost achieves the best performance with R-squared 0.54, indicating that it could explain over half the variance in cognitive frailty progression. The top 5 feature importance identified according to XGBoost are the changes in albumin levels, changes in red cell distribution width, changes in chloride concentration, changes in eosinophil count, and changes in total calcium. So here's the performance summary for gut microbiome-based classification. We can see that the class level achieved the best performance using LightGBM model with F1 score of 0.67. This shows that class level offers the best trade-off between feature richness and noise. The top 5 microbial classes based on the LightGBM models are negative acutes, Verrucomicrobi, gamma proteobacteria, Bacteroidia, and Actinobacteria. In conclusion, we can see that the models showed moderate performance, highlighting the need for larger, more diverse datasets and further feature refinement to ensure clinical reliability. Recommendations for future work would be expanding dataset size and diversity by increasing population variability to improve generalizability and reduce overfitting. The second recommendation is to combine blood and microbiome data. Multi-model inputs can improve predictive strength via complementary pathways. The third recommendation is to adopt longitudinal microbiome sampling. It enables dynamic modeling of fertility progression over time. The fourth is to validate key biomarkers biologically by using lab testing or targeted sequencing to confirm clinical relevance. In summary, this study lays the groundwork for scalable, interpretable, and biological grounded AI models in aging and fertility care.